In today's video, we will look at two characteristics of vector spaces known as span and linear independence. We will begin by defining what we mean by the span of a vector space or a spanning set. We will then look at some properties of spanning sets. We will then move on to define what we mean by linear independence and look at some properties of linear independence. So the goal in the next two videos is to study a way of describing a vector space. So many real vector spaces contain a finite subset of vectors that can be used to completely describe every vector in the vector space. This subset happens to not necessarily be unique. So when studying this subset, two important characteristics arise: a spanning set, and that set being linearly independent. First, we define what we mean by a linear combination. So a vector v in a vector space is a linear combination of the vectors u1, u2, so on and so forth through uk in V, when V can be written in this form: C1 times U1 plus C2 times U2, so on and so forth, plus CK times UK, where C1 through CK are scalars. So we're going to consider this set of three vectors in R3. We're given two vectors, v and w, in which we want to write each one as a linear combination of the vectors in S. So what we'll do is we will call these vectors u1, u2, and u3 respectively. Okay. So for v, we want to write v as a linear combination of those three. So c1 u1 plus c2 u2 plus c3 u3 for constant c1, c2, and c3. These are the constants that we have to determine. Well, if we actually write this out, this means that we want to write the vector 1, 1, 1 as c1 times the vector 1, 2, 3 plus c2 times the vector 0, 1, 2 plus c3 times the vector negative 1, 0, 1. Well, if we look at this, right, this would mean that c1 times 1 minus, so c1 minus c3 would have to be 1, 2c1 plus c2 has to be 1, and then 3c1 plus 2c2 plus c3 has to be 1. This is a linear set, right? It's a linear system, rather. And we saw how to solve that by setting up a matrix. Right, that's our coefficient matrix, and we augment it with our constant matrix, which in this case is the vector 1, 1, 1. And then we would perform row reduction on it. So I'm going to use that symbol to represent is row equivalent to a specific matrix. So what we want to do is now row reduce this matrix. And I'm going to show you how we can do this using technology. So we come over to our calculator, and we want to row reduce a matrix. The command for row reduction is RREF. Now we just have to create our matrix. We come over to menu. We want number 7. Create a matrix. Number of rows, we have a matrix of 3 rows and 4 columns. And now just enter our values. which was 1, 0, -1, 1, 2, 1, 0, 1, and then 3, 2, 1, 1, and then just hit enter, and there is our row-reduced matrix. So this matrix is row equivalent to this. So reading this matrix, we find that C1 is equal to 1 plus C3, and that C2 is equal to -1 minus 2 C3, where C3 can be any real number. So why not set it equal to 1? And we can say that V is equal to 2U1, right? 1 plus 1, minus 3U2, and then plus U3. Now for W, we want to play the same game. Right? So we want to write W as some constant times U1 plus some constant times U2 plus some constant times U3. Now to set up this, we're going to take each vector in S and write it as a column of our augmented matrix. So we're going to have first column as 1, 2, 3, second column as 0, 1, 2, third as -1, 0, 1. Now we're augmenting it with W, which is 1, -2, 2. We want to RREF this. So 3, 2, 1. And when we RREF this, oops, I'm missing parentheses. We get this matrix here. Right, now notice this last row. That says that 0 is equal to 1, which of course we all know is nonsense. So we can conclude that this equation, this system, has no solution. So we cannot express W as a linear combination of the vectors in S. So we'll just say of the set S. Now, the set of all linear combinations of vectors S equals the set U1, U2, so on and so forth up through UK in a vector space is called the span of S, denoted by span S. If span S is equal to V, then S is said to be a spanning set of V, or simply that S spans V. Right, so again, the set of all linear combinations of the vectors of a set S is called the span of S, and if the span of S happens to be the entire vector space, then we say that S spans V. So we look here and we say S is the set t plus t cubed, -1 plus t squared, and t. And we're asked if S spans P3. Right, so first, recall that P3 is the set of all polynomials of degree 3 or less. So it's the set of at cubed plus bt squared plus ct plus d such that a, b, c, and d are real numbers. So here's what we want to do. We want to write any arbitrary vector in P3 as a linear combination of the vectors in S. And the question is, does this have a solution? To make things easier, let's go ahead and group like terms. So we'll get c1t cubed plus c2t squared plus the quantity of c1 plus c3 times t, and then plus a negative c2. Right, so this breaks down to c1 has to equal a, c2 has to equal b, c1 plus c3 has to equal c, and negative c2 has to equal d. Well, this can be written as this augmented matrix and we can take a look at this. This is going to be row equivalent to some matrix. Let's figure out what matrix it is. And so this time we have 4 rows and 4 columns. And it's important here to notice these A, B, C, and D are all italicized, not bolded. If it winds up being bolded, that means that you have that value stored as something. You'll want to clear out that value first. Right? And that is done by clear AZ. Right, so if we REF this, we get the identity matrix, and this is just simply saying this alert. If we take a look at it, domain might be larger than the domain of the input, so it's just saying that the domain that they gave may not be the domain of our original input. It doesn't really mean anything for our purposes. Well, again, if we look, this last row is a bit of a problem. Right, that says that 0 equals 1. Right, which means that we cannot express every single polynomial of degree 3 or less as a linear combination of these vectors. So what we say is, therefore, our set S does not span P3. Now, it could span some subset of P3, and in fact it does span a subset of P3, but it does not span all of P3. Okay. Now, if we let S be a set of vectors in a vector space, then the span of S is a subspace of V. And so, remember, we have to prove three things. We have to show that it's a non-empty subset of V. Then we have to show that it's closed under addition and closed under scalar multiplication. Well, by definition, span of S is a subset of the vector space. If we set all the constants equal to 0, we get that 0 is in the span of S, which means that S is non-empty. Now we just have to prove that it's closed under the two operations. So let's consider two vectors, call them V and W, that are in S, or in the span of S, rather. I don't know why I put parentheses there. Then what this means is we can write V as a linear combination of U1 through UK, of the vectors in S, and we can write W as a linear combination of the same vectors. So we can write V plus W as C1U1 plus so on and so forth plus CK UK, and then plus D1U1 plus so on and so forth plus DK UK. Grouping terms together, we can write this as C1 plus D1 times U1 plus so on and so forth CK plus DK times UK. Which of course can be written as E1U1 plus so on and so forth plus EK UK for E sub I equaling CI plus DI. Right now, this clearly is a linear combination of the vectors in S. So we can conclude that V plus W is in the span of S. Now what we say is we let gamma be some real number. Then, if we look at gamma times V, right, this is gamma times C1U1, right, so on and so forth, plus CKUK, which is gamma C1U1 plus so on and so forth, plus gamma CK UK, and we can write this as F1 U1 plus so on and so forth plus FK UK for F sub I equaling gamma times C sub I. Right? And again, this is clearly a linear combination of the vectors in S. And so gamma V is also in the span of S. So we have now shown that span of S is closed under addition and closed under scalar multiplication. Therefore, the span of S is a subspace of V. Now if we let S be a set of vectors U1, U2, so on and so forth, UK plus 1, so on and so forth, UN, be vectors in a vector space V. If S1, which is the vectors U1 through UK, spans V, then S also spans V. In other words, If you have a spanning set and you add vectors to it, the result also is a spanning set. Now, since S1 spans V, then for any vector V in V, there exists constants C1 up through CK, right? Such that V is equal to C1U1 plus so on and so forth, plus CK UK. It's a linear combination. But we can write this, we can write this as C1U1 plus so on and so forth, plus CK UK plus 0 UK plus 1, plus so on and so forth, plus 0 UN. Well, this is still a linear combination of the vectors in S now. So therefore, S also spans V. Right? We wrote V as a linear combination of the vectors in S. So simply by adding vectors to a spanning set doesn't change the fact that it is a spanning set. Right? Now let S be a set of vectors in a vector space V. We say that S is linearly independent if the only solution to this system is the trivial solution. If if that system has a non-trivial solution, then S is said to be linearly dependent. And so in other words, if you're to write the additive identity as a linear combination of the vectors in S, then the only way you could do that is if all of the constants were 0. Any other way of writing the additive identity means it's a linearly dependent set. So we're looking here at 3 vectors in the vector space M22. We're asked if they are linearly independent. All right, so remember, M22 is the set of all 2 by 2 matrices. So we want to check the solution to this system. Equals the additive identity in M22, which is the 2 by 2 zero matrix. Writing this as a system, we'll get that C1 plus C3 has to be 0. C2 has to be 0. C2 has to be 0. And then C1 minus C3 has to be 0. Now this is actually easy enough to solve without use of Gaussian elimination. However, just to see how to do it, we're going to go ahead and set up the matrix anyway. And remember, we want to augment this with our vector. And we wish to RREF this. All right, so this time we have a 4 by 4 again. REF it, and this is the matrix that we get. Notice that this matrix says that C1 equals 0, C2 equals 0, C3 equals 0. So it's only trivial solution we have, so therefore we say that they are indeed linearly independent. Now if we let S be a set of n vectors in Rn, and we let A be the matrix whose columns are the elements of S, then S is linearly independent if and only if the determinant of A is non-zero. Right, so let's first suppose that S is linearly independent. Then it follows that the row-reduced echelon form of A is In, which means that A is row equivalent to In, which, if you recall, means that the determinant of A is non-zero. Now, conversely, if the determinant of A is non-zero, then recall that this means that A has to be row equivalent to In. Now assume that the columns of A are linearly dependent. Then it would follow that the RREF of A has a row of zeros. However, this is a contradiction. This contradicts the fact that A is row equivalent to the identity matrix. Therefore, S must be linearly independent. Right? Because if it was linearly dependent, we reach the contradiction. This proves both directions, so the proof is complete. Let U1 and U2 be vectors in a vector space V. The set of just U1 is linearly dependent if and only if it's the zero vector. The set of U1, U2 is linearly dependent if and only if at least one of the vectors is a scalar multiple of the other. All right, so first to prove the first statement. Now we have already proven that if C1, U1 is equal to 0, right, then either C1 is 0 or U1 is 0. However, assuming linear dependence of the set of just U1 implies that C1 can be non-zero. This means that U1 has to be 0. Conversely, if U1 is 0, then C1 equals 1, which is of course not 0, leads to u1 being 0, which of course means that the set of just u1 is linearly dependent. And so the first statement's been proven. Second statement. If u1 and u2 are linearly dependent, then C1 u1 plus C2 u2 is equal to 0 has non-trivial solution. If C1 does not equal 0, then C1 u1 plus C2 u2 plus negative C2 u2 is equal to 0 plus negative C2 u2. Right, which means that C1 u1 plus the quantity of C2 u2 plus negative C2 u2 is equal to just negative C2 u2, which means that C1 u1 plus the additive identity is equal to negative C2 u2, which of course means that C1 u1 is equal to negative C2 u2, which means that C1 u1 is negative 1 times C2 u2, which means that C1 u1 is negative C2 times u2, which means that 1 over C1 times C1 u1 is negative C2 over C1 times u2. Of course, this then means that 1 u1 is negative C2 over C1 u2, and 1 u1 is just u1. And just for clarification, let's put parentheses around all those. Likewise, if C2 is non-zero, we find that U2 is negative C1 over C2 times U1. So one of the vectors is a scalar multiple of the other. Now, if U1 is a scalar multiple of U2, we can write 1 U1 plus negative D U2 is equal to 0. Similarly, if U2, I'm sorry, this should have been minus DU1. Similarly, if U2 is DU1, we can write that negative D U2 plus 1 U2 is equal to 0. And this proves that the set of U1 and U2 is linearly dependent. And that proves the second statement. Now let S be an indexed set of M vectors in a vector space V if there exists a linearly dependent subset of S. Then S is linearly dependent. So first we note that rearranging vectors in an index set does not affect the set's linear independence. Since the rearrangement of terms in the system C1U1 plus so on and so forth plus CK UK is equal to 0 leads to an equivalent system. Now let us rearrange the vectors in S as necessary so that the vectors U1 through UK are the elements of the linearly dependent subset. Of S. Let's suppose the remaining vectors of S are UK plus 1 through UN, M. Then C1U1 plus C2U2 plus so on and so forth plus CKUK plus CK plus 1 UK plus 1 plus so on and so forth plus CM UM. Oh, I'm sorry, this should be 0 UK plus 1 and then up through 0 UM is equal to 0. Where C1 through CK are not all 0 because U1 up through UK are linearly dependent. Now this of course applies that S is linearly dependent. Alright, so as a corollary, let S be an index set of vectors in a vector space V. Right, two statements. If at least one of the vectors in S is 0, then S is linearly dependent. If a vector appears more than once in S, then S is linearly dependent. And this follows directly from theorems 4 and 5. So instead, let's now look at proving theorem 6. For an integer k greater than 1, the vectors u1 through uk in a vector space V are linearly dependent if and only if at least one of them can be expressed as a linear combination of the remaining vectors. So if u1 through uk are linearly dependent. Then there exists constants c1 through ck, not all zero, such that c1u1 plus ck uk is equal to 0. Let cj be one of the non-zero coefficients. Then c1u1 plus so on and so forth plus cj minus 1 uj minus 1 plus cj uj plus cj plus 1 uj plus 1 plus so on and so forth plus ck uk equals 0. Right, means that we can write this. Which means we can write this. Right? And we're allowed to divide because cj is non-zero. Conversely, if it is possible to express ui as a linear combination of the remaining vectors, we have ui is equal to d1u1 plus so on and so forth plus di minus 1 ui minus 1 plus di plus 1 ui plus 1 plus so on and so forth plus dk uk, which means that we can have d1u1 plus so on and so forth plus di minus 1 ui minus 1 plus negative 1 times ui plus di plus 1 ui plus 1 plus so on and so forth plus dk uk equal to 0. Which implies that u1 through uk are linearly dependent, right? Because negative 1 is non-zero. Now we want to show that this set is linearly dependent, and then write one of the vectors in S as a linear combination of the others. So setting up our vector, I'm going to say this is our first vector, second vector, third vector, and finally fourth vector. Right, so let's set it up. We're going to have this matrix, right, where if you notice each column represents a vector and each row represents a coefficient. First row is of t squared, second row is of t, third row is of the constant. Now let's see what we get when we row reduce this. Right, so we get this matrix right here. Right, this of course implies that S is linearly dependent, right? We have C1 in terms of C4 and C2 also in terms of C4, where C4 is not necessarily 0. Right, so if we write this out, we're going to get that C1 equals C4, C2 equals negative C4, and C3 must be 0. Well, if we write this out, right, we get C4U1 minus C4U2 plus C4U4 is equal to 0. Right, if we set C4 equal to 1, we will get that U1 minus U2 plus U4 is 0. Right, so U4 is negative U1 plus U2. So writing this out now, where we have our U1 through U4, let's write t minus t squared is equal to negative 1 plus t squared plus 1 plus t. And there's our linear combination. And we conclude with a theorem that is all through without proof, theorem number 7, which says the vectors u1 through uk in a vector space is linearly dependent if and only if one of these two statements is true. U1 is 0, or at least one of the vectors can be expressed as a linear combination of the preceding vectors. Right now, in fact, one can be extended to if any of the vectors in the set is the additive identity, then it's linearly dependent. Right? And this is a natural extension to, what was it, theorem number 4. So that concludes this video on span and linear independence. In the next video, we are going to look at a set that perfectly describes a vector space. And of course, that set's going to have the properties of span and linear independence. This set is called the basis of the vector space. As always, I thank you for watching this video. I hope you've learned something, and I will see you all in the next video.